Today I choose complex analysis. Okay, because in quantum mechanics in chemistry, in theoretical chemistry, means we encountered almost now and then with complex functions. Like in quantum mechanics, wave function is inherently complex. Then we use Laplace and Fourier transformation. Those are also defined in terms of complex plane. Okay. And then extension of Fourier transformation to FFT that requires the knowledge of complex plane. Okay, the root of unity. And in means I want to share two story means which inspire me to learn these things. This is important, but this has not been taught in our mathematics in chemistry or any other things in chemistry. So in one class from Professor Theory semi-classical mechanics. So he in some derivation he used the Cauchy-Riemann identity. So that time I realized that it is important to know. Otherwise, this step almost goes blindly for me. Then in one class of solid state chemistry in physics department, they are in the derivation of some Thomas Fermi model. There was the use of this complex function, and they used this for any complex analytic function, means its derivative with respect to z bar. If z is a complex function, its derivative with respect to z bar, this complementary function, this is 0. So from this derivation goes just straightforward. But why this derivative with respect to z bar, this equal to 0, that was not means that was blurred to me. And again in the electrodynamics, there we encountered many times the Poisson's equation, Poisson-Boltzmann equation. There we need complex function very much. In spectroscopy, in the Fermi-Golden rule, in that derivation, that Himangsu just take that part, this delta function, but this delta actually comes from this integration of sine square x by x square, this kind of thing. So if we stay in the real axis, those integration to solve this integration is very much difficult. So sometimes we could not find any way how to solve it. But if we go into the complex plane, then it is just a few lines means in the complex plane. Then we come to the rotation. Okay. In the rotation, this requires in the 2D rotation in 2D plane, we need the complex plane. Otherwise, there is a very tricky way to do it. Means everybody in animation, to make animation, they use the complex plane. In the 3D rotation, we need to use some extended complex plane. This is quaternion. This is another interesting topic. So complex function is everywhere in mathematics and mainly in physics. So we need to know that. Otherwise, in our upcoming discussion also, that the path integral derivation, semi-classical mechanics there, and also this Kubo correlation function, all those we need complex. We need to know about how to handle these complex functions. And these whenever we start with some differential equation, this complex function saves our life very much, because there we take Fourier or Laplace transformation and transform it algebraic equation. Now we after solving it in that space, Fourier or Laplace space, we need to go back to that original space, real space. So we need, in that integral, in that inverse transformation, we need to know how to integrate this complex function. So it is one of the most important topic, means that we need to devote some time and learn it. Then it will simplify our lives a lot. So then first we start, means I will means touch the important topics in this complex analysis, means which is important for our theoretical chemistry or physics community. And then I will show one application is Kramer's tonic. Again another important topic in spectroscopy, because this is a very fundamental relation, does not depends on the property of material or anything. So it depends on the cause and effect relationship, causality, but nothing else. So now I start this complex analysis. This, we know, in the complex plane is defined by real plane and an real axis and imaginary axis. Okay. If my cursor is not visible, please tell me. This is real axis and imaginary axis. And if fz is analytic in a domain D, okay, domain is inside this complex plane. Okay. If fz is single valued and finite derivative in this plane, then fz is called analytic. Okay. So it is very much similar to the real, for our real axis, real function also. But we saw that we in the following topics, these complex functions are much easy to handle compared to real functions. So if this derivative in this domain exists, then fz is analytic. Okay. So fz means, if we now write fz, if my function is fz equal to z bar, its complementary function, then z bar equal to x minus iy. Now z equal to x plus iy. So this is not analytic. This is an example of this when this is not analytic. Okay, z bar is not analytic function of z. Okay, so why this is so? Because this derivative does not exist. Now in the complex plane, derivative means at the limit of z tends to 0. Okay, now in the complex plane, we can approach del z tends to 0 in many ways, in many directions. So means derivative should be defined in such a way that it should not depend on the directions. Okay, it is independent of the direction. So means if we follow the real axis and make del z tends to 0, then it should be equal to if one follow the imaginary axis and make del z tends to 0. So limit del z tends to 0. This is the identity for the derivative. How we write the derivative in terms of limit. Okay, this is the known. Now let's follow this is del z bar. If we write this fz plus del z minus fz, so this is del z bar by del z. So del x minus del y I divided by del x plus del yi. Okay, this is simple. Now if we approach del z tends to 0 from real axis, what will happen? Then in real axis del y equal to 0. So this is del x by del x. This is equal to plus 1. Now if one follow del z tends to 0 from imaginary axis, where del x equal to 0, then minus, this will be minus del y and here will be plus del yi. So this is minus 1. So this is different path. Here different path, if we choose different path, it provide different result. hence this derivative does not exist. Similarly, in real axis also, if we follow the negative way in the real axis, so and if one follow the positive way of the real axis, there it should be match. Otherwise, if they don't match, the limit itself does not exist. That's why in real axis is defined. If we want to extend it in complex plane, then there are different directions, not only positive and negative. So they are also if the result change, then this derivative doesn't exist. It is not analytic. So means here for a function to be analytic, the derivative must be same for the two paths on real and imaginary axis. Okay. So fz we can write in general is a real part and imaginary part. So this is real part is a function of, this is a real function of u and x, and this is a real function. V is a real function of x and y. Okay. So del f del z equal to limit del z tends to 0. This is as we also shown in earlier. This is del u plus I del v by del x plus I del y. Okay. Now, similar way, if we approach through real axis towards del z tends to 0, then we have this del u del x plus I del v del y. Okay, just del y equal to 0. Put del y equal to 0 and make the limit del x tends to 0. Now, if we follow the imaginary axis, then del x equal to 0, put del x equal to 0 and take this limit del y tends to 0. Then this is del v del y minus I del u del y. This is very similar as we shown earlier in the last example. Now, this f to be analytic, df dz, it has to be a value, means it is defined. It should be defined in this complex plane. So in this domain. So if this to be exist, then these two paths have to be same result, have to provide same result. Then this real part of these two approaches should be same. If these to be same, real part should be same and imaginary part should be same separately. So del u del x equal to del v del y, and del u del x equal to del v del y here, and del u del y equal to minus del v del x. This is Cauchy-Riemann relation. So this is very important relation. So you can note it down. Also note that earlier observation that del f z del z bar. Okay, this complex with respect to this complex conjugate. This if this is equal to 0, then this derivative exists. This is analytic. Okay, so here are a few examples. So this is polynomial of z to the power n. So this is analytic, and e to the power z, cos z, sin z means all those function means who has a Taylor expansion. Those are means Taylor expansion we will discuss in detail. It is very important. So these functions are analytic. Fz equal to 1 by z is analytic everywhere except z equal to 0. Means here the function explodes to infinity. So except that point, it is analytic everywhere. Now, fz, if fz is analytic, fz equal to u x plus iy plus iv is a function of x comma iy. So if fz is analytic, u and v both are twice differentiable. Then means if these two conditions followed, then del u del x, then Cauchy-Riemann equation, if fz is analytic, then from the Cauchy-Riemann equation, Cauchy-Riemann identity 1, del u del x equal to del v del y, and del u del y equal to minus del v del x. Then if we take the differentiation with respect to x, this Cauchy-Riemann 1, then we get del 2u del x2 equal to del 2v del x del y. Then Cauchy-Riemann from Cauchy-Riemann equation 2, if we take the differential with respect to y, then del 2u del y2 equal to minus del 2v del x del y. Then if we add these two things, then this will cancel out. Then we get del 2u del x2 plus del 2u del y2 equal to 0. So this is Laplacian of u equal to 0. When Laplacian of some function equal to 0, not u is now real. This is my real equation. So we derived it from complex via this complex plane in this simple way. So this is a very important property, important class of the function. This is when u is a harmonic function, when Laplacian equal to 0. In heat equation, this kind of things appears, and also in chemistry, in saddle points, in one direction it is one direction it is positive and other direction it is negative. So this del 2u, one direction curvature is positive, one direction curvature is negative. So in saddle point in chemistry, this harmonic function appears. So this is an important property we derived from this Cauchy-Riemann equation. Now take these two functions, two real functions, fx equal to mod x, means we can, this is differentiable. This is fx is continuous but not differentiable at x equal to 0. Now we can make it continuous, means if we take these functions x mod x, it is differentiable. It is differentiable at x equal to 0, but not differentiable for the second times, means this is differentiable. Okay. Now if we differentiate this, we get mod x, then this cannot be differentiable. Okay. So for real function, this is one most important thing in complex plane, and this makes, means this tells why complex, why handle the function in complex plane is too easy compared to real plane. So here is the example. A function x mod x. Okay, everybody is, I am audible? Everybody could follow?
Yes, yes.
Okay. Just stop me whenever you need question or confusion, anything. So in the real function, it is x mod x. Okay, this is differentiable, but it is not differentiable for the second times. Okay, so we could not expand it in terms of Taylor expansion. So if we know a value a some point, we cannot reach the other point. So because after first differentiation, the derivative does not exist. But for the complex plane, if fz, for the complex function fz, if fz is analytic, all its derivatives are also analytic. Okay, all its derivatives exist. If fz exist in some domain, in some complex domain, okay, then if we know value at one point in that domain, we can reach to the other point through this Taylor expansion. Okay, how we can prove that? This is important. This is one important property of this analytic function. This makes this makes life so simple that people tempted to extend the derivation in the complex plane and then again come back to the real plane, just taking the real value after this derivation. So let's consider fz equal to u plus iv as before. Fz is analytic, then Cauchy-Riemann equation ux equal to vy and ui equal to minus vx. Okay, Cauchy-Riemann equation 1 and 2. Now we take the first derivative ux equal to ivx. Okay, now we can write f prime, this is capital U, this is capital V. Okay, so from Cauchy-Riemann equation, if f prime, from Cauchy-Riemann equation, now we don't know f prime is exist, okay, but we don't know f prime is differentiable or not. Now we apply Cauchy-Riemann equation on f, okay, because it is analytic and it is differentiable. So ux equal to vy. So we can take the derivative with respect to x, then ux equal to vyx, and then Cauchy-Riemann equation to vx equal to minus uy, then we can write capital Vy equal to small vxy. Okay, so these two are same. Okay, so ux equal to Vy we get from here. This is the Cauchy-Riemann equation for f prime we derived. Then uy equal to, then again if we take differentiation with respect to y here and differentiation with respect to x here, we will derive uy equal to minus vx. This is Cauchy-Riemann 2. So we derive this f prime f means this derivative of f, first derivative of f prime, it also follow the Cauchy-Riemann equation. So first derivative of z is also analytic. Again we can apply for the second derivative of x in the same way. So we means it is trivially shown that all these later on derivatives are also analytic if fz is analytic. Here we only assume that fz is analytic. Okay, so this makes our life simple, because if we if in some domain if fz is analytic, then from one point we can travel to all other point in that domain by this Taylor expansion. So the functions are nice. Integral means next, these are the property we will use again and again. So now we need to know how to do integration in the complex plane. fz, similarly fz is as before, fz is u plus iv. Now for the integration we need some path. Okay, this is a path is called contour, and this is a direction, means from the left side or right side here, or from clockwise or anti-clockwise. It is the normal convention. So for clockwise it is negative, for anti-clockwise it is positive. It is the direction of the path. So this is the, we need to define the path. So along this path we need to integrate this fz. Okay, means we take integration means similar summation over all those points. Now here this is the important property of this integration, which is called Cauchy-Gorset theorem. Means don't need to remember that, but this property is very important. fz is analytic in a simple closed curve. This is fz is analytic within D. This is fz is analytic inside here, this D domain. Now we have a simple closed curve. Okay, now integration in this closed curve we can write in this way: this cyclic integration of fz dz. This will be always 0. Okay, if this curve is closed and it is inside analytic everywhere, then always for any closed curve this is equal to 0. So how do we prove it? This is very important. Means if you don't remember also it derivation, but this property is means extremely important. This inside this inside analytic function, if we take any closed curve, it is 0. So this fz dz, we can expand it u means u dx, u plus iv, and z to dx plus I dy. Then we can separate it out, the real part and imaginary part. Okay, now this is a line integral. If we consider first the real part of the integration, this is the line integral. So this line integral we can transform it into the surface integral. Means surface integral. This is the so-called Green theorem. Now this means physical understanding is that this line, if we take the integration along this line, and if we separately do, if we do means instead of that, if we divide this whole part into small segment, this whole surface, and take the divergence of each part, each small part in that surface, then this all the intermediate divergence cancel out, and we will get only this line integration. So line integration to surface integration, we have to take this divergence and sum it up along the surface. So just to illustrate, we do not here is the proof of the Green's theorem. So we can illustrate, means this can be illustrated in this figure. So these are the small divergence over all this surface. Okay, if we add this divergence, means integrate over all this surface, this all the intermediate flow are cancelled out. So we get flow in the boundary only. So this is the line integration, and this is the line integration. Resultant is the line integration, but we can derive it from the surface integration also. Okay, so that means in general, this is divergence of this f. Okay, or for all this surface, means throughout this surface, equal to line integration along this boundary line. Okay, so if we put this for this f is a vector and ds is also vector, dx dy, we get easily this identity, line integration to surface integration. This is Green's theorem. So from this surface integral is required because then we can see the Cauchy-Riemann condition. By Cauchy-Riemann condition, this is 0, and from this Cauchy-Riemann condition 2, this is equal to 0. Okay, so this whole cyclic integral for this of this complex function is equal to 0 inside this complex plane, inside this analytic region. So this is this is very important relations. So everywhere we if we define some, means if we imagine very large domain, and if it is analytic there is 0, no matter how large it is, the domain is. So here is an important property, means I can go here. Here is an important property. If we, means this immediately reminds us what we read in thermodynamics. Okay, means in thermodynamics, for this for any state function, the cyclic integral is 0. Okay, means for work also, means if we do a work, means in a cyclic displacement, if we then total work is equal to 0. Okay, if we apply a force and make a displacement which is cyclic, so this work is 0. So for any kind of state function, so fz is similar to the state function what we learned in thermodynamics. So in this way we can visualize the things. So for the state function, we know that from one state to another state, if we draw any arbitrary path, all the result will be the same. So fz dz, if we follow this c1 path, this equal to fz dz if we follow the c2 path, means this is equal to this. Also we can derive from this fact, this cyclic integral equal to 0, because then we can, this is the c1 and c2 minus c2, we can write it here. So this total equation equal to 0. This is the cyclic integral. If we divide this whole integration into the two parts, c1 and minus c2, then this c1 and minus c2 we can write it. If we invert the arrow, the integration value will change its sign. So if we invert the arrow, there will be minus sign here in front. So this equal to this integration along c1 path equal to integration along c2 path. So both are equivalent. Okay, this is like state function, and here I put the example like work. Okay, so like a conservative vector field. So u equal to, if a gradient of some potential. So okay, then we can, if this gradient, if we calculate this gradient of phi dr, if we follow any path, any arbitrary path, all the result will be same. Okay, this will be phi r1 minus phi r2. This will depend only on these initial and final points, not on the path. Okay, this is an important topic of this complex integration. Now we know that inside that complex plane, it is if we follow any path c1, c2, any closed path, it will be 0. But the interesting thing happens, means mostly in the real examples, in the most cases, there are some singularities there inside that. Okay. So this integration is not equal to integration has a finite value. So this is the main theorem. Okay, this is not equal to 0, but this C1 C2, this is in between C1 and C2. This region is analytic. Okay, so we can deform this region, means arbitrarily. That's why this C1 integration over the C1 and integration over the C2 both are the same. Okay, inside there is singularity. If we do not touch this singularity and deform this curve, C1 and C2 curve, in arbitrary way, the result will be same always. Remember, we should not touch the singularity. Okay, then we cannot derive it. This expression is not valid. If we don't touch the singularity, if we take any arbitrary curve, means which encompass the singularity, both the integration will be same. How do we prove it? So we can similarly we can just join. Inside it is analytic, so we can just dig a tunnel, basically, means just to close these two contour, C1 and C2, to join these two contour and just reverse its sign. Okay, so this overall is the closed curve. Okay, because inside it is analytic. Okay, where we can deform it, it is analytic. So in this closed curve, it is 0 because of this earlier theorem that inside the closed curve, this is 0. If we encompass this analytic, this contour, in the analytic region, okay, this closed integration is 0. So there it is C1, and if we see the direction of this contour, this is minus C2. Here this is anti-clockwise way, this is plus. So here this is clockwise way, this is minus. So this overall closed contour is defined by two closed contour. This is inside is C1 and outside is C2. Okay, this point is clear? Hello?
Yes.
Yes.
Yeah, means here we can make this tunnel area very small and small. In the limiting case, when tunnel area tends to 0, this exactly equal to, means this contour, C1 contour plus minus C2 contour. Okay, now we can get this minus C2 contour, means in the opposite side, in the right side, and this is normal minus, these minus signs will go out, and this C1 contour, fz, integration of fz along this C1 contour equal to integration of fz along this C2 contour. Okay, so but this is not equal to 0. Okay, this total is equal to 0 in this C1 minus C2 contour. Total is equal to 0, but individually it is not equal to 0. It has a value. So this is a important another important theorem, the most important theorem. I say, means here this, if there is no singularity, we can if we draw any arbitrary contour, any arbitrary closed contour, integration will be always 0. If there is singularities, if we do not touch the singularities and encompass the singularities, then we can deform the contour in any arbitrary way, and the result will always be same. So we can deform it in our convenient way, in our convenient shape, where we have nice expression for this contour curve also. We will see that. The use of that means here. Suppose this is a contour, okay. We can deform this inside it. There is no singularity. Okay, we can deform it in any way, and we can deform it and goes to a point, sinks to a point. Point means that integration is 0. So this is 0. So we can derive this thing from based on from this theorem, if we remember only this theorem, this singularity one. We can back derive it. And there is another means nice use of this kind of property, means we can sink it in arbitrary way. So there is an arbitrary contour, we can sink it in a unit circle. It is same, the total integration will be same. So but unit circle, we have a nice property here. This unit circle, we can apply this Euler theorem. This z equal to unit circle, this any point on this contour z equal to e to the power I theta. Okay, this Euler theorem. So here dz equal to e to the power I theta, I d theta. Okay, so we need to evaluate this kind of we are interested to evaluate this kind of function z to the power n, fz equal to z to the power n dz. Okay, inside this for this contour. Okay, z to the power n dz. Okay, this is the result. We came to this result. So z to the power n dz. So we put e to the power I theta for the z. So it is e to the power n I theta, and from here I theta, from dz there is one more I theta. So e to the power n plus 1 I theta, I d theta. Okay. So for any n, any positive n, okay. So for any positive n or 0, n value, n can have value of 0, 1, 2, anything. So here we can see that this integration, this whole contour integration goes from 0 to infinity, the limit of this contour. Okay. So this is a trivial integration and this is 0, because this sine cos sine has similar positive area as that of negative, and also for the cos function. So this is 0. This is very trivial. Now come to the non-trivial case. When there is a singularity, then also we can shrink it to a circle, but not shrink it to that point. This is not 0. So for this circle, we can again apply z equal to e to the power I theta, and e to the power I theta I dz equal to this. Means this is not singularity. This is means at 0, this is singular. Means the one example is 1 by z to the power n plus 1 at z equal to 0 for any positive n. For z equal to 0, then it explode to infinity at the origin. Okay. Now, if we put this expression for this contour, Euler expression, then it is e to the power I theta, e to the power n plus 1 I theta. Okay. Then we get d theta e to the power, this I theta cancelled, e to the power minus n I theta. Okay. Now, what is the value of this expression? If for n not equal to 0, then we again get sine cos, integration for sine cos. This should be equal to 0. So this is equal to 0 for n not equal to 0. Okay. Now for n equal to 0, this is non-zero. Okay. For n not equal to 0, this term is 1 and this is 2 pi. So this is 2 pi I. Okay. So this is very important result here. So for this, for z to the power n here, if we integrate z to the power n in a region, in an analytic region, then it is equal to 0. If we integrate, z to the power n is analytic. However, 1 by z to the power n plus 1 is not analytic. So if we integrate over this contour, which encompass this singularity, this is analytic everywhere except this z equal to 0. So if our contour encompass this singular point, then what is the value here? This is means non-trivial one compared to earlier one. Means if this is non-zero for n equal to 0, for n not equal to 0, it is 0. Okay, this is, I am telling it several times because means this is very important building blocks for this complex integration, whole complex integration. If you forget all the previous things, just remember this thing. This also would be enough for this complex integration. So we can write it in this way. So this is the dz divided by z to the power n plus 1, and this contour is encompass this singularity. Okay, so if we take 1 by 2 pi, this is a delta function. It is which is 0 for all other n and non-zero 1 for n equal to 0. Okay, if we have this kind of means singularity at z, if it is singular, this function is singular at z equal to a, means in general way you can write it dz by z minus a whole to the power n plus 1. So it is also similar, same. This delta means it is 0 for all other n except n equal to 0. Okay, so now we see here, if we substitute n equal to 0, then this is dz by z. So for dz by z means this is non-zero, this is 2 pi I, this integration is 2 pi I, but dz by z square, dz by z cube, dz by z to the power 4, all are equal to 0, although they also have singular points inside that. So dz by z is a special thing, so we call it as residue. Okay, we come into that part. Means dz by z, just remember that if we have all kind of singularity, means 1 by z, 1 by z square, 1 by z cube, 1 by z to the power 4, means no matter whatever be the term in the denominator, but only we need to focus this first order term, this 1 by z. So then means we can forget all other things, because all other things give 0 after integration. So in general way, we can means we know that any analytic function we can express in terms of Taylor expansion. Like if it is analytic, then fz equal to ak z minus z1. We can expand around z minus z1 in terms of Taylor expansion. Okay, so whole to the power k. But if there is a singular point there, then this Taylor expansion is not sufficient. This generalized form means we have to extend this concept. So this is called Laurent expansion. This Laurent expansion is similar to the Taylor expansion, but in the Taylor expansion we expand in terms of polynomial of z, but in other parts we have to take account the singularity. We have to take expansion in terms of polynomials of 1 by z. Okay, here is the polynomial of 1 by z. Okay, this is the Taylor expansion, means ak means this we can derive in terms of derivative of fz. Okay, first derivative, second derivative, and this is basically Taylor expansion is basically right in terms of polynomial of z around this function, around some point. But if this point is singular, then we need another function which is a function of 1 by z. So 1 by z minus, here z1 is singular, so here it is 1 by z minus z1 plus 1 by z minus z1 square. This is the Taylor expansion, this is Laurent expansion. This takes account the singularity. Okay, this is a function of z minus z1, this is the function of 1 by z minus z1. So now this is a general form of any function, means it is even if it is not analytic everywhere, means it is a singular point here. So we will means this kind of expansion is useful in general for any kind of complex function. So we need to integrate, we need to calculate the integration around this contour C1, okay, which encompass this singular point Z1. Okay, so if we take the integration around this closed contour, there is two integration part. One is for this Taylor part, this normal analytic part, and this is not Laurent. This is the principal part, we say, the non-analytic part. So non-analytic part for Laurent, for the analytic part, this is 0, by Cauchy's theorem, we see that for any analytic function, if we define a closed contour, this is equal to 0. And for the non-analytic part, means all other part will be 0. The all other integration will be 0 except this first order part, z minus z1, that we have seen earlier. So all other parts equal to 0. Then this whole integration of fz, integration of this whole fz, it reduced to the integration of this first order part only. Okay. So what is this value of this integration? We just learn in the last phase. This value of this integration when n equal to 0 means 1 by z. What is the value of this integration? This is 2 pi I. Okay. So we just use this. This is b11 is a constant, and this remaining integration is 2 pi I. 2 pi I b11. Then b11, then this integration we can write it in terms of this 2 pi I b11. b11 is the coefficient of this first order part of 1 by z expansion. So this is called residue. Okay, because this is the most important part in the complex integration. So if there is any value of the complex integral, it comes from this residue. This is the coefficient of the first order term of the 1 by z expansion. Okay, this is called residue. So if we know the residue of this function, okay, then we know the integration over any closed contour. This is the Cauchy's integral formula. This is the main formula we use everywhere, means wherever we do any complex integration. So this is the main part of our main part is finished for today's talk. Main mathematical parts. Now small things we need to know to handle this real problem. This, please note this part, means integration of this closed contour, means even if it encompasses any singularity, we just have to calculate the residue at this singular point. At z equal to 8 is singular. We have to calculate this residue at this singular point and just multiply it with 2 pi I. That is equal to the integration along this contour. So how to find residue? Next practical parts, the main mathematical things are done. That's to handle how to handle practical examples. So this is the Lorentz series. This is the analytic part, Taylor part, and 1 by z expansion of 1 by z. This is the principal part. So this is the residue. This is our main interest to calculate the integration. So we have to calculate the residue. This is the gist. So if we find the residue, then the integration is done basically. Let's say, for example, sine z by z square. Okay. So what is the residue for that? Means sine z is analytic, so we can expand in terms of Taylor expansion. Z minus zq by 3 factorial plus z to the power 5 by 5 factorial. So this by z square, we get 1 by z here. They are very, we can see we can see visually what is the residue here. Residue is 1. Okay, the coefficient of 1 by z is 1. It is singular at z equal to 0. So first we need to identify what is the singular point there, and then within that region, what is the singular point inside that region. Okay, first we need to identify that, and next work is we need to find out the residue at that singular point. Okay, these are the two tasks is done, then integration is done. Then this is another technique. This is just technique by observation. We can just see that what is the residue. Another technique when we could not easily visualize what is the coefficient of 1 by z. Then how do we do it? Then finding the residues around there might be a simple pole. Here it is a 1 by z. This is a first order term, means we call it simple pole. Means pole is not simple when there is z 1 by z square, 1 by z cube. Okay, all other higher order 1 by z expansion. Okay, so when we have only simple pole like this, only 1 by z part, not 1 by z square, 1 by z cube part, then we can find the residue easily by this technique. We can first, means we know that if we know that if z is singular at z equal to z naught, then, and it has a simple pole, means only first order part of 1 by z, then what we can do, we can take do a multiplication of fz with z minus z naught and put z equal to z naught, means take the limit z equal to z naught. So this is equal to the residue. So very simple derivation here. So here this is the general function. Now we consider the example for simple pole when only 1 by z part exists. So 1 by z minus z naught part exists because we consider our singular point at z naught. So only this part exists. So this is our function. Okay. So we do that trick, z minus z naught, multiply z minus z naught. So multiply z by z minus z naught, that leads to, this is k plus 1 and this is b1. Now if we put z tends to z naught, means z equal to z naught here, then this whole function, this gets to 0 because of z minus z naught there, and this is equal to b1. So this is very easy to show why this trick works. Now find, now there is an example, cos z by z to the power 4 minus 1. Okay. Now z at z equal to y, we know that this is singular, this explode to infinity at z equal to y. So we need to calculate the residue at z equal to y. Okay. So we can expand it in expand this z to the power 4 minus 1. Okay, this z plus 1 z minus 1, there is z plus I z minus I. Okay, so we know that here we know that this term appears only once. So it is a simple pole with respect to this singular point I. Okay, so this is a simple pole. So to know that, to get the coefficient, we can apply the same trick. But here this coefficient is not clear by only by inspection, only by expansion, not so clear. So we can use this trick, just apply with z minus I, then z minus I gets cancelled. Okay. Now then put z tends to I. Okay, if we put z tends to I, this is cos I by 4i. Now cos I we can evaluate in terms of this Euler's formula. Okay, e to the power e plus a to the power minus 1 divided by 2. So residue at z equal to I equal to this. Okay, very simple, very simple. Means this, to handle these complex things are very simple. Its name is complex. This Professor theories also mentioned that this name complex, but it is simple and real. This important, means this trick also important in other purpose also. Means if this equal to 0, if z minus z1, if z this equal to 0, then we know that there is no b1 term also. Means this is totally analytic. So we can use this trick to know that if fz is analytic or not at z equal at any point at z naught here. If it is infinity, then we know that z naught is a higher order pole. If it has higher order terms, 1 by z minus z naught square, then there would be also z minus z naught term here, 1 by. So it would be infinity at z tends to z naught. So if it is infinity, then this term is infinity, goes to infinity. Then if z has higher order pole, if it is non-zero and finite, okay, like here b1, then we do have a simple pole at z equal to z naught. Then we can use this treatment to get the residue. Now for the second part, if this is infinity, if this has higher order pole, then how do we get the residue there? Then there is a means another trick here. No more trick, only two tricks. means mainly we use is trick pole one. We encountered with pole one example, but if sometimes we encountered other pole higher order pole also, there we means fz as a pole at fz is singular at z equal to z0, and it has a non-simple pole. Non-simple pole and non-order, it has order n. Its pole has order n. So 1 by z minus z naught whole to the power n, like that. So we take a integer m which should be greater equal to n, means it can be equal to n or otherwise it should be greater than n, this order of the pole. So we take z minus z naught whole to the power m. Earlier we take z minus z naught only and multiply with fz. Here we take z minus z naught whole to the power m. Now take the derivative m minus 1 derivative of this whole quantity. Okay. Now the residue is, if we take this derivative in this limit z equal to z naught and divided it by 1 by m minus 1 factorial, okay, then we get the residue. It might looks complicated, but if you see the derivation, it is very simple. That's why I put the derivation. This is the normal expansion, Laurent expansion of fz. Okay, so when z0 is a pole of order n, okay, so this Laurent expansion stops at n, okay, because it has order n. So step 1 is we multiplied z minus z naught to the power m. Okay, z minus z naught to the power m, that will for the analytic part, normal Taylor part, it will give m plus k, z minus z naught to the power m plus k. This is still analytic, and all this part, because m is greater equal to n, there is no denominator part. All takes to all comes to the numerator. Then this is m minus 1, m minus 2 up to m minus n. Okay, it all the part, because m is greater equal to n. That's why this condition is required to bring all those denominator into numerator. Now take the differentiation with respect to m minus 1. Okay, if we take differentiation m minus nth differentiation, then we take then we get this all other m minus 2 is less than m minus 1. So if we take differentiation at m minus for m minus 1th time, then this part will be 0 again. In the same, for the same reason, all these m minus 2 to m minus n term, this goes to 0. Okay, and here if we take the differentiation m minus 1th differentiation, then we get only b1, and there is a factor m minus 1 factorial, because every time we differentiate, this coefficient comes as a multiplication. Okay, so but this part remains analytic. Okay, there is no m part here, that doesn't matter, but main important part is that this part remains analytic. So if we put z equal to z naught, then this analytic part goes to 0, and this is equal to b1. b1 is the residue, and m minus 1 factorial. So what is the residue here? This 1 minus m factorial, this m minus 1 differentiation of the function multiplied by z minus z0 whole to the power n. Okay. Now an example here. Z cos z, z minus pi q. This has a third order. This it is in that it is third order pole. Means by inspection we can see that. So first we multiply. We can take 3 or 4, n equal to 3 or 4, and here it is seen. It is obvious. So that's why we take just n. Z minus pi. We multiply z minus pi whole to the power 3 with this fz. This is z cos z. Now we take derivative d2z dz2, means 3 minus 1 times derivative, d2 dz2 of these whole things. So we get this minus 2 sin z, means just the product rule, and we have to put the limit z equal to pi after that. So it is just pi. Okay, now divide it by 3 minus 1 factorial, n minus 1 factorial, 3 minus 1 factorial. So this is 2. So residue of this is pi by 2, which is not simple. Means in either in expansion, or if we expand it, it would be much more difficult. But if we use this trick by just 2 or 3 lines, how to calculate this residue. Now this is all the tricks here. Now we go to the direct example of this contour integration in the practical use. Means how we can use this contour integration to simplify our life when we encountered with any complex, not complex means not complex, complicated, any complicated real integration. So this complex plane, extending to the complex plane, and use the property of this analytic function, that makes our lives a lot easy. So up to that point, if anyone have any, now we saw the examples, we go into the example part. So that's why I want to pause 2 minutes here, 1 or 2 minutes, if anyone have any. Hello. Hello.
Yeah,
Hello. It is.
yeah, I think it's fine for now.
Okay. Then okay, we can, because if anything you have doubt in mind, just clear it now. Otherwise, it will be simple. It will be then straightforward for you to follow the examples, the real life examples. So most important thing, that's why I wanted to recap again the Cauchy-Riemann theorem that we will encounter many times in other purpose. We will not show it today, but I believe that we find it importance in whenever we handle the complex function in quantum mechanics or semi-classical mechanics. And the second important thing is that this contour integration, the theorem of residue, means in the singular for a function, in the real function, in the practical purpose, whatever function we use, it mostly have singular points. So for the singular points, we need to worry only about the residue. So first we calculate the residue, then it's done. This integration is done. Okay. So today we will talk more about that prospect of this integration. So this is one example, minus infinity to plus infinity, dx by x square plus 1. This is normal integration. No, this is in real integration of some real function. So this kind of integration, if we consider, if we extend it in the complex plane, then we get it makes it's simple, its derivation a lot, that we will see here. Now we just extend it in the complex plane. Here, this is the real part, this is the imaginary part. Imaginary axis, this is the real axis, and we have to calculate the actually we need to know, we have to know what is the value along this of the integration along this real line. But we can define it in the we can extend in the complex plane in terms of, we can write it in terms of z, means extend it in terms of in the complex plane, and we can close it in the through the imaginary. We can take this closed contour means through this imaginary axis. Okay, means this now this whole integral is a complex integral. Okay. Now we can write this whole integral in this splitted way. This is the real part, what we need to calculate earlier, and this is the other part, arc part. Okay, this we call arc part of this integration. Now, by this means this left side of this left side integral is very trivial, means trivial from this earlier theorem, is residue theorem. Means we need to know the residue. There is one singular point. There is one singular point. If we use this very arc of very large radius, is that I will tell why we do not use this small arc and why this very large arc. Okay, if we use this very large arc, then it encompasses a singular point at z equal to y. At z equal to y, this is infinity. This function is infinity. So what is the value of this closed integral? This is the just 2 pi I and residue of this function at I. So what is the residue of this function at I? This is a simple pole, 1 by z minus I, z plus I into z minus I. So multiply with z minus I and just put z equal to I here after that. Z tends to I. So 1 by 2 pi and these 2i cancel. So this is equal to pi. Now we need to evaluate this part also. So dz by z square plus 1 through this large arc. So if we make the arc very large, means if we make the radius of the arc very large, tends to infinity, then it will, all the points have 1 by r square term. This is summation of all the points at the infinite limit. So it has 1 by r square term. So all the points at the infinite limit along this arc, this is equal to 0. Okay. So this part equal to 0 and this part equal to pi. So this is mainly a two-line. Just we need to find the residue. And this handling of the arc is very easy. So this is just pi. Okay. Minus infinity to infinity dx by square plus 1 equal to pi. Next example is cos x by 4x square plus 1. Okay. So this is, we can use the Euler's theorem and rewrite it, this integration, in terms of e to the power ix, and if we take the real part, this is the cos x. Means in the spectroscopy, many times we use this trick, this Euler expansion. So here we focus this integration, dx e to the power ix by 4x square plus 1. So we can, similar way, we can extend it in the complex plane. So dz means this contour integral, dz e to the power iz 4z square plus 1. This is this integration that we need, and this integration along this arc, this complex integration. So again, this encompass a singular point. Okay, this encompass a residue. So residue at z equal to I by 2. We can encompass in, by the way, we can encompass in other way also, means result will be the same. Because there the contour sign, we have to take care about the contour sign, but then it takes care about the sign of this whole integration, plus or minus. Okay, now come back to this. This for this contour, we need to find the residue at z equal to I by 2. Again, we can see that this is a simple pole. We can easily see that. So we just multiply it by z minus I by 2. Then at the denominator, z plus I by 2 remains, and then put z equal to I by 2 here. Then we get e to the power 2 pi I root t by 4i. Okay. Now this arc part 1 by 4z square plus 1. We already in that this tends to 0, but we need to take care of this e to the power iz part. What about it is by iz part at infinite radius limit of this curvature? At infinite radius limit, z equal to I alpha means IR. We can say it is nomenclature notation should be same. Z equal to IR at this complex arc. Okay, so z equal to IR. If we put z equal to IR here, okay, it will be e to the power minus r. So at r tends to infinity, when radius of the arc is infinity, e to the power minus r tends to 0. This is a very important trick. Means e to the power iz. If there is e to the power iz part, so in e to the power it tends to 0 in the upper half plane. But if it is e to the power minus iz part, it tends to 0 at the lower half plane. It is very important where we deal with the time propagator in quantum mechanics and try to solve it in terms of Green function. Okay, this kind of things appears again and again. Means when the things converge, where the things converge in the upper half plane, when it has e to the power iz part, and when it has e to the power minus iz part, we need to take into account we need to deal in the lower half plane. In the Kramer's conic also, we have similar kind of things. I will show you. Now, again, another example, dx sine x by x. Dx sine x by x. And here, this is I equal to if I take in the same approach, if I take Euler expansion e to the power ix, then I prime equal to minus infinity to infinity e to the power ix by x. If we take imaginary part, then we get our integral I. Okay, so first we derive this I prime integral and take the imaginary part. Then I prime integral, it has another difficulties which was not there earlier. It is singular at x equal to z. Okay, so we can calculate this. We can define this integration this way. Means we can calculate this integral. Means only see the real line. Along this is x-axis, real axis. So if we take, we can write this whole integration minus infinity to infinity in terms of minus infinity to minus epsilon and epsilon to infinity in two parts. And if we let this epsilon tends to 0, then this whole summation means converge towards this I prime integral. Okay, this is a small trick to avoid this small singularity. So that means we need to calculate the principal value. It is called, in the mathematical language, it is called the principal value of this part. When it has a singular, when in the real axis, the function, we need to calculate the integration on the real axis, and in one point the function is singular. Then we need to skip this point, skip only this point, but we calculate it all these points except that one point. Then this is equal to I prime. So this is called principal value for a function, for an integral. So now we define this contour. We skip. Now we need to skip this singular point. Okay, if singular point was in the upper half plane, then it is okay. But problem arises, it is the singular point is seated in the real axis. That's why the problem arises. So we cannot go through the pass through the singular point. We need to skip it anyway. So we skip it here. This gamma 1 is mainly the principal integration, principal line, and gamma 3 is required to skip it by a half circle. And again, gamma 2 is the earlier familiar arc part. Okay, now for this whole integration, we need to calculate the integration parts by parts. This is whole integration, means this in this closed contour. This is equal to 0, by the way. There is no inside this closed contour, gamma 1, gamma 3, gamma 1, gamma 2, gamma 3, gamma 1, gamma 3, gamma 2. Inside this closed contour, there is no singular point. So this is 0. So this integration equal to integration along this principal line gamma 1 and integration along this gamma 2 and integration along this half circle. Okay. And we make this radius of the half circle very small, epsilon tends to infinity. Okay. So we first calculate what is the value of this integration on this half circle. So we can just, if we remember the residue theorem, this is just directly came from the residue theorem. This, if it is full circle, then it encompass only one singular point. So then its value is just residue at that point. Okay. Now we can again rederive it, means just like earlier, e to the power epsilon e to the power I theta. Here, this circle line, we can derive it in terms of Euler expansion, epsilon e to the power I theta. If we put epsilon e to the power I theta into this expression, there is dz, by the way. So e to the power epsilon I theta and epsilon e to the power I theta, I epsilon e to the power I theta d theta. Okay. So then it get cancelled and this epsilon tends to 0. This is equal to e to the power I 0, e to the power 0, that is equal to 1. So whole terms is I d theta. That means it is 0 to pi. It is minus I pi. Okay. So this minus term appears because of this. There is a minus. Minus term appears because if we take there is a opposite sign. There is a clockwise notation of this contour direction. The contour direction is the anti-clockwise direction. We get plus I pi. Okay. What was the earlier, according to the earlier convention? We can also found from this residue theorem. Residue theorem means what is the residue of, means if we complete this full circle, then what is the value of this integration along this full circle? We need to calculate the residue. Residue at this singular point. Residue at this z equal to 0. Residue is e to the power iz. Okay. This is the residue. Then we can put it, it will be just e to the power I pi. Residue is just 1 by z. If we expand e to the power iz, this is only, residue is only 1. So this is 2 pi I. So half circle, for half circle, it area would be also half. It is pi I. And for this opposite sign, it is minus pi I pi. Okay. So this kind of half circle thing, if we encounter any singularity at the real on the real axis, we have no option. We have to just take the principal value. Anyway, means we have to either bypass it in the up circle in this way or in the opposite way. Both would give the same result. So this whole integration, come back to this whole integration. Whole integration is means gamma 1 along this principal line, gamma 3 and this gamma 2. This we divided into these 3 different lines, the 3 different segments, this whole integration. Inside that there is no singular point. This is equal to 0, and this integration along this principal axis, this is our deserved. This is our deserved integration. I prime. Okay, here. Now here along this gamma 2, this is when arc radius is infinity, this also goes to 0 because 1 by r is also tends to 0, and here e to the power ix in the upper half plane, it goes to 0. E to the power iz in the upper half plane, it also goes to 0 when r tends to infinity. We have shown here. So this arc part also tends to 0, and this part, this small part that is needed to skip the singular point. So this is minus I pi. So we just, what is the I prime now? I prime is equal to I pi. So we need to take the imaginary part. Imaginary part is just the imaginary. What is the imaginary part? Imaginary part of I prime is pi. Okay. So this is our integration pi. So this is equal to pi. So I have not shown here, but also similar way we can calculate this sine square x by x square also. That is means that is required for Fermi-Golden rule. Okay. This integration we need to evaluate this integration to derive the Fermi-Golden rule. This is one of the basic principle of the spectroscopy. So today we will mostly focus in this application linear response. In the linear
Lakshya,
response, huh?
so it is almost 2. So I think could we discuss in the next week or so?
Yeah, this is just take 5 minutes.
Okay.
Because you know already, means there are all the derivations, so there is nothing new here. So just to show the examples here. So linear response, we know that if there is a stimulus or force Ft, okay, there is a retardant response, means this is a kernel. Kernel depends on this t minus t prime due to the retarded response. Okay. So if we measure at t time, we need to, means the effect came from any previous time, not the time from future. So this is cause and effect relationship or causal response. Okay. So this is RT. This is normal linear response expression. This our measured response is equal to is linearly dependent on the stimulus or force, external force, and this is the response function that we also seen in the earlier discussion here. And this is phi t. Okay, phi t is called the response function. So in the Fourier space, this is our this is in the Fourier space we can this is just the Fourier transform r tilde omega, and this is the Fourier transform of f tilde omega. So we can write it in terms of Fourier expansion, rt equal to Fourier transform of r tilde omega, and f equal to Fourier transformation of f tilde omega. We can rearrange these things and take the t minus t prime equal to tau. So we have after rearrangement we have e to the power it f tilde omega and d phi, and phi t we have e to the power I omega tau. So here we can e to the power in the left hand side e to the power I omega t, in the right hand side e to the power I omega t d omega. So we can put it in one side and get it common, d omega e to the power I omega t. So this is the part, remaining part, this equal to 0. So this for this equal to 0 as e to the power I omega t are orthogonal, these bases are orthogonal. So if this equal to 0, so then the coefficient should be 0 for each omega, each and every omega. So this r tilde omega equal to this. Okay. So r tilde omega is linearly in the Fourier space. We can see that it is just proportional to f tilde omega, and r tilde omega equal to chi omega f omega. Okay. Chi omega is the generalized susceptibility. Now chi omega equal to 0 to infinity dt e to the power I omega t phi t from this relationship. So due to causality, now here this is 0 to infinity. Okay, this 0 actually appears due to causality. Okay, because here it is a upper bound t. So if we convert it into the into this new variable, we find a lower bound at 0. So this comes from the causality. This Fourier Laplace transformation, we already know that. That's why I just go through it quickly. This itself, this expression has a symmetry. This if we take minus omega, then its real part has this kind of symmetry, and imaginary part has this kind of symmetry. Means this is just very trivial from this. Okay, Now, hello, hello.
Yeah, I can hear you.
Yeah, actually, sir also called. That's why I just get disconnected from the flow. So, can we take more 5 minutes, or I can also explain it? This is just a very quick example. Is it okay?
Yeah, I think you can share the notes also, and we can.
Yeah. Just quickly go through and just share the note.
Fine.
Yeah. Just chi omega exist here. This chi omega exist means if phi t means the external force have some is some dragging force. It contains some dragging part e to the power like e to the power minus gamma t. Then we can take this dragging part into this e to the into this phi t, into this phi t here. Just this dragging part from this ft here. We can bring this dragging part into this phi t here, and then also our susceptibility is well defined. Okay, how it is well defined means this dragging part is minus gamma t that we borrow from this stimulus. Okay, external force. So if we this is means if we get it common, means I common, then omega plus I gamma. Okay, so if this there is a minus e to the power minus gamma t, then only it exists. If it is e to the power plus gamma t, then it explodes. It does not exist. So for e to the power minus gamma t, this function exists. So if we take I common, then e to the power it is I gamma. So it is exist for this positive imaginary axis. Okay, this gamma should be positive. If gamma is negative, then it is not exist. So imaginary gamma in the upper half plane, if we consider frequency, if we want to extend the susceptibility in the imaginary space, we need to stay it in the upper half plane. We cannot go into this down plane. Means this why we need to go in the upper half plane means because in some cases the force might be like the friction force or dragging force e to the power minus gamma t. Then it is convenient, or it is much easy to handle it in the complex plane. Okay, like in the Laplace transformation and Fourier transformation. Laplace transformation, we need this extra part here, and Fourier transformation, we have only imaginary part. So this this chi omega is analytic function in the upper half plane. Now we consider a function chi omega part. This is chi omega is singular everywhere. Okay, but if we make it non-singular at omega equal to omega prime equal to omega. Okay, so by dividing it, this chi omega divided by omega prime by omega, this function, now this function f omega prime is diverging at omega equal to omega prime. So at omega equal to omega prime means at some point omega, this is omega prime, real omega prime, this is imaginary omega prime. At omega is real. Okay, now at omega equal to omega prime, the function diverges to infinity. But any upper half plane, this if we take any integration, this is 0. Now if we consider the similar like of contour, this principal, taking the principal value and just skipping this singular point and taking this r. So this principal value minus r to r. Okay, so d omega prime. So this is equal to d omega prime chi omega prime. This is omega prime minus omega. This is the principal value on this real axis. And in this similar way, this is this half circle. This half circle is for gamma 2, and we can get it from the residue theorem. It is simply from the residue theorem. It is simply I pi into 2 pi I into at that value function. What is the value of the residue at that singular point? This is I pi chi omega. Okay, we can also derive it from, this is very same. That's why I'm not going into step by step. So arc part tends to 0 because there is e to the power gamma t part, and in the upper half plane, if there is an exponential function, it is tends to 0. And so this whole contour integration is equal to 0 because inside it is analytic, there is no singular point. So we divided it here into principal part and arc part and the semicircle part. So arc part is 0, so principal part is equal to semicircle part, small semicircle part that we avoid due to singularity. So chi omega equal to then principal part, this small semicircle part, there is chi omega appears because of this residue of this function at this singular point. This coefficient is chi omega. This is simple fold. Coefficient is chi omega. So I pi chi omega. This is the value of this integration. So this chi omega is now then equal to this principal value of this integration along this real line. So we need to do the integration and skip this only this singular point. So this is my expression. So from here we can just take the real part of it. Then there is I part sitting in front. So real part is equal to the some integration of this imaginary part. And imaginary part is equal to the some integration of real part. So these two parts here is constrained with this integration. So that's why it is called a Hilbert transform pair. Okay. So if we measure in the physical, in our chemistry example, physics example, optics example, means real part of susceptibility is related to the dissipation and imaginary part of the susceptibility is related to the attenuation or absorption. So whenever we measure absorption, susceptibility, absorptive part of susceptibility, and we measure the real part of susceptibility, this we need to check whether this Kramer-Skorny relationship is followed or not, because it does not depends on any mechanism of the material or media. It is just a mathematical relation. So it should be valid. Otherwise, there is some problem in the measurement or some parts we have not taken into account. This is very important for nowadays for nanotechnology, where we have very little access. Means sometimes we can access the dispersion more easily. Sometimes we can access the absorption more easily. So there we can get the other part by using this Kramer-Skorny relation. So this is for optics. This is a huge importance. This has a huge importance. Means just like Fermi-Golden forms the basics and basics for the theory, but for the experimentalist as well as theoretician, this Kramer-Skorny relationship is one of the most fundamental relations that I will say. So if anybody has any question, they can also ask.
Bhaiya, I have a very quick question. Can you go back to Cauchy's integral?
Yeah.
No, I think it is the formula of that Cauchy's integral.
Acha, Cauchy's integral.
Yeah.
Yeah, here. Here.
That integration of fz into z dz is equal to 2 pi I something.
Acha, with residue.
Yeah.
Residue theorem. Yeah, this is 2 pi I. Yes.
So this formula is applicable for this if we have only single singularity. Now suppose if we have two or more than two singularities.
Yeah. Your
like
question.
one by
Yeah.
z minus a into z minus b, then what will be the
See that example. Yes. See that example here. Okay. It has z plus 1, z minus 1.
plus 1 minus
If we encompass if our contour encompass only one pole, then this is simply just residue of that. Okay. If it is encompass multiple pole, okay, we can apply the same things for that with respect to that pole also. Okay. Hello.
Okay, so it's
So it
like
is
this,
it
just
is
some
just
sum of.
summation. It is just sum of all
Okay,
those
okay,
integration. Yes, sum of all those
okay.
integration. If I encompass, if my contour encompass z equal to 1 also, along with z equal to I, so we need to do integration with respect to z equal to I residue, and plus we need to do integration z equal to 1 residue. Okay. Okay, just can I draw here? Okay, here. Okay, so can you see my drawing?
Yes, it is visible.
Okay, so there are my two residue. Okay, two singularities, and my whole contour is this. Okay, right. Now we can we can we can deform this contour anyway. We can deform this contour.
Hmm.
That we can do.
Mm-hmm.
We can deform this contour. We can deform this contour. Okay, and then we can deform this contour like this way. There are two singularity. Okay, we can deform this contour this way. Okay, so this whole integration is divided into these two integration. All right. Just joining this tunnel. We can divide in this way. Just they touch each other.
Mm-hmm.
Okay. Is it clear? Hello. Mm-hmm.
It is clear.
So this is some of all these integration with respect to individual residue. This is written as a separate theorem, but I did not discuss because this is just trivial from this. So any more questions? Questions? Because I feel that topic is important because in the next we are talking so many times that semi-classical mechanics is important, path integral is important, UVO formulation is important, and we need to go deep into this spectroscopic response function. They are inherently those things are complex. Just here, Fermi-Golden and Kramers-Kronig are the only two examples, two fundamental examples. But if we go deep and deep, there we need much more to handle the complex things, complex functions. Okay.
Okay, so you can now stop the recording, I
Yes,
think.
yes, yeah.